So let's begin. I want to pick up about where we were last time. We'll study this example. I did say something that was incorrect last time, so it's worth thinking about. I want to go through that example a little bit more, and then I'll go through this example that we're all pretty familiar with, and we know good estimators for mu and sigma squared. And we're going to see different ways to derive these things and different ways to think about the estimators themselves. I'm going to do a very rough attempt at generalizing everything we've done for the last couple of days as to where these estimators come from, and I want to point to some pitfalls. And then I want to discuss those pitfalls in terms of the examples that we're familiar with. After we get done with this, I want to move to the EM section of the book. So there's an algorithm in the book called expectation maximization. That's the EM algorithm. So you can tell a statistician named that algorithm. So why? Because it tells you exactly what it is. So it could have a cooler name. This algorithm is the basis for variational Bayesian algorithms. So if you've ever heard anybody do some MCMC or something like that and somebody says, why don't you try variational Bayes? It's an approximate technique where they build an approximation in. They don't do Markov chain Monte Carlo or something like that. That could be slow depending on the proposal that you pick. That's always the name of the game in MCMC, is how do you pick that proposal. We've got a little tiny bit of experience with that. Variational Bayes makes a assumption, a simplifying assumption about the distribution that you're trying to study. They make it so it's factorizable. So I'll just point out, as we have it written down, a normal is not factorizable in those two parameters. I'll say something about that when we write out the likelihood function. X bar and S squared factorize, but mu and sigma squared do not factorize. So there's a big difference there. And then they run the EM algorithm over the top of it. And so they don't tell you that in any paper. Usually they inundate you with a bunch of measure theory first before telling you it's something you already know. So we're going to be studying the EM algorithm. I think that'll take about 2 or 3 lectures to go through. So if you want to get started on that, that's coming next time. Just a heads up, I am going to have you implement the algorithm in kind of a simplified form, and you'll do a simulation study as well. The nice thing about this simulation study is you're only going to be studying one method under various conditions. So you won't be comparing 3 different things. So it's a little bit less arduous. EM algorithm has some math up front though. It's not like bootstrapping where there's no math involved. You do have to work out math, and then you need to code up that math. And so that means that there can always be mistakes, as you're doing something. So when I first code up my anything, there's some error. And the question is it a bug, some typo, or do I actually have the math incorrect? And so that can be very tricky. So say that, we'll study it, I'll work out the math for you on the problem that you're gonna be applying this to. So that's all coming. Okay, I want to just say something about MOMs versus MLEs versus Bayes and what the book says about this, and it's not quite complete. So I want to generalize a little bit further. So method of moments operators are matching empirical moments to theoretical moments. It's not specific about which moments you match. And in fact, they don't actually have to be moments themselves. So they just need to be functions of moments. And that's what I want to generalize for you in a couple examples. So method of moments, the way the book writes it, I'll just abbreviate this MOMS from now on. So this is from the book. So this is the technique. So imagine I have some parameter space. Parameters in these examples, so the parameters in this example are theta. It appears twice in this distribution. And the parameters in this model are mu and sigma squared. So there's 2 parameters here and there's 1 parameter here. So in general, consider we've got some parameter that we want to estimate. And I'll just write this down as theta 1, theta 2 to theta p. So it's a p-dimensional parameter space. In example 1, there's a one-dimensional parameter space. And in example 2, there's a two-parameter parameter space. In the model that we're going to be studying is xi comes from some density function. I'll imagine this could be a mass function. And those underlying parameters govern it. And the name of the game for us in a parametric inference class is to estimate those parameters. So here's the technique as outlined in the book. What they do is they come up with the empirical moment. And then they write down the theoretical moments, and then they do a match. So the idea is this. Write down your empirical first moment. And so that's going to look like this. It's just x bar. I goes from 1 to n. And I'm going to match that to the empirical moment. And I have to work this thing out up front. Dx, integrate over all of x. So you work this out, you get that, and eventually we're going to match those. I'll say something about that last step in a moment. The second moment looks like this. I'll suppress my indexing, but this goes from I to n, and I match that to the second moment. And then I continue down, and I do this for the pth moment. So the empirical pth moment from your data is easy to calculate, and potentially this is easy to calculate. So you just do that all the way down. And the idea is what you end up doing is you match the moments. Match moments. So this is step 1. Step 2 is you're going to solve for theta. Thetas, I'll say theta i's, I goes from 1 to p. And you're going to re-nickname these theta hats. You won't leave them in terms of theta because they're estimators. And so, and rename theta i's, theta hat i's, to denote their estimators. So essentially you're just going to do this. Sum of the xi's over n is going to be equal to expectation of x. The expectation of x is going to be a function over theta. So usually I'll write in bar theta to denote that that's a function of theta. Expectations are always a function of what they're conditioned on. They're not functions of the x's because the x's have been integrated out. And so I'm going to take my thetas and I'm going to set them equal to theta hat right there. And that's the notation that I'll use to denote that. And that's the notation I used in your earlier simulation study. A couple of you came and asked, what does this all mean? We'll see what it means through these examples in a second. So I'm going to just do that all the way down. P is equal to the expectation of xp. And I'm going to just take these and call them the theta hats. Of course, I'm going to take theta 1 and make it theta 1 hat, just to be specific. And that's method of moments. This could be a good idea or a terrible idea. It seems to work in some examples. It's a very heuristic thing. There's no theory that says this is going to work out for you. The generalization to this is you don't have to match your first p moments per se. You can match any p moments. The idea is that you've got p parameters that you're solving for, so you need p equations to solve for it. There's a theorem that you learned in algebra that says that that's true. So you're going to need p equations to solve for p unknowns. There's no guarantee that all of these expectations in order actually have the thetas in them. And we've seen that in this example, and we'll come back around to it. I want to also point out, this can really be functions of the moments as well. So you don't actually need the x's right here, but rather I could do things like, I'm going to take an expectation of some function of x, and I'll solve for that in terms of theta, and then I'll solve for that. So this in terms of a branch of inference gives an infinite collection of non-unique answers. Some will be better than others. So that's one thing I know. If two things are different, one of them is presumably better than the other in some cases. Method of moments doesn't say anything theoretically about whether or not this is a good idea. And in the book, they give you an example where when you solve for theta, theta is even outside of its domain. So it lives somewhere else, and so it gives a nonsensical answer. Maximum likelihood estimators. So they give unique answers if the maximum likelihood is unique. And so just like any maximization problem, if the maximum is unique, there's a global maximum, then that's what the MLE is solving for. What they discuss in the book, I'll say a little bit about it, but this is basically your first semester of calculus. So maybe your second semester of calculus when you do this multivariate-wise. So there's nothing different here. So MLEs, again, a statistician named this because it tells you exactly what the procedure is. So maximum likelihood basically just maximizes the likelihood function. So in the book, where they start out telling you about this technique is they usually do something like this, where you're going to take your 5 partial derivatives of your likelihood function. You're going to do this for I goes from 1 to p. So you're going to take all of your p partial derivatives and you're going to set them equal to 0. And after you do that and you solve for the thetas, you're going to take your thetas and you're going to match them to theta hat. And you're going to re-nickname them theta hats. Possibly you come up with the same answers over here. Maybe you come up with something entirely different. And so the book talks about this. It tells you you need to check for saddle points, so you might need to do a second derivative test. I'll let you read through that paragraph in the book, but they talk about it in terms of a 2-parameter space. And they tell you to work out the second derivative matrix, all of the mixed partials. So the second derivatives on the diagonal, your mixed partials in the off diagonal, that's called a Hessian matrix. So a Hessian matrix has all of your mixed partial derivatives. So in the context of theta being p dimensional, it's going to be a p by p matrix. In the problem that they're studying in the book, they're using p is equal to 2, and they tell you you're supposed to take the determinant of that, and you want to check a condition on the determinant. Does anybody remember what the condition is from the book, if you've read through it already? It says it needs to be positive. It's actually talking about the eigenvalues in that case. So in a 2-dimensional space, if all of a sudden both eigenvalues are positive, something like that, then all of a sudden you have something that looks like a paraboloid. It doesn't have any inflections in it. If it's negative, in a negative eigenvalue, that paraboloid is flipped upside down. So it's convex. That only works for a two-dimensional space. Really, it's just another incarnation of the second derivative test. And so realistically, you just need to make sure that when you solve this, you set it equal to 0, you're not in a salad. All that same stuff you learned about a long time ago. You also need to check on the boundary of the space. So the boundary of the space won't be differentiable, presumably. You'll be slamming into something, and you can't take a derivative there, and so this condition isn't finding the solution there. You need to make sure that on the boundaries, you don't have maximums there. This is all out the door if you can't differentiate the likelihood function. So I'll just make a note, make sure likelihood is differentiable if you're going to do this technique. Check saddle points. So I'll say second derivatives. And the boundary. Anybody study optimization in this class for a living? I don't think so. So a lot of people do. And so they just study optimization. So in an OR department or an ISE, that's the name of the game. And statisticians are a little bit similar to that. They're going to say a little bit more about this, and they're going to try to quantify uncertainties around everything. But Unley could tell us maximization problems are harder than I'm making it sound. So this is a special class of maximization. When you can do this, there's all kinds of optimization problems that are much, much harder than this. And so ultimately, you want to take the likelihood function and maximize it, and it could be a lot harder than this sort of an algorithm. So depending on the space that you're studying. If it's disconnected, there's a lot of partitions or something like that, you can't just do this. So if you're going to run a maximization algorithm like Newton-Raphson or something like EM, you need to check all of the conditions that you've converged to that maximum. That's still all true. So you can port everything you know about optimization and slide it right into this lecture. So buried class here. So whole class or whole PhD. So again, these could be complicated problems. The maximum likelihood kind of has an advantage over method of moments in that whatever the answer I come up with is going to be something where theta actually lives, because the likelihood is going to constrain it to build that in. The moments themselves don't have that constraint built in. And so the likelihood function is also always conditional on every sufficient statistic. And so it's going to have the sufficient statistics built in. It could be the case that the moments are the sufficient statistics, and if the moments are the sufficient statistics, this might be following the sufficiency principle, but there's no guarantee. This is guaranteed to follow the sufficiency principle, and it's also conditioning on the data. And so following this sort of technique is not a violation of the likelihood principle. Following that paradigm is a violation of the likelihood principle, even though in some cases these could come up with the same answers. Let's look at a couple examples. Try to clarify this. Brendan, how much do you know about Bayes?
Not much.
So you won't learn too much in this lecture either, but I'll say a few things in a moment. We'll also study Bayesian solutions as well. We do need to study decision theory before we can understand exactly what the Bayes estimators are, but think of it as something like there's some estimator out of your posterior distribution, whether it be a mean, a median, a mode, something like that. So you're at liberty to change the objective function that you're optimizing. In the next couple of weeks, we'll formalize all of that and see what the ramifications of those choices are. Okay, so example 1. So 1, xi's come from a uniform. All my examples are IIDs, so I'll suppress that. So last time we wrote down a moment-based solution, I'm going to use all n data points this time, just so that we can extend what we did last time just a little bit. So if I take the expectation of x, we know that's 0. So a uniform distribution between minus theta and theta, the expectation is right in the middle. You can do the calculation if you'd like, but I think we can all see that through safety. And so the expectation of the first moment, that's just going to look like this. Expectation of the xi's divided by n, I can factorize all that out. Everything's IID, so I can get rid of my I. This thing's still 0. So those are all zeros. And so this first moment won't help you any. So if I were following exactly what the book says, I'm already a little bit stuck because my first moment isn't of any help. And what they would probably recommend, although they're not explicit about this, is you just shift down the moments that you're looking at. Again, there's no general theory on which moments you're supposed to match. It changes for every problem. I think the way they motivate this in the book, the sentence I read, was sometimes this is a good technique if no other techniques present themselves. I don't know what that means, because techniques never present themselves. So I've never had a technique like walk into my office and say, here I am. So use me. So I don't know, maybe this is a last resort sort of thing. So I tend to think it's just a good idea to compare against this and see what goes wrong. So it's the way I think about this. So then you might match the second moment. So the x squared, just one data point. We know what this is. This is the interval length squared divided by 12. So I can't forget that from my first probability class either. Nobody ever remembers the numerator. It's the interval length squared because they always start you out with a uniform distribution between 0 and 1. So 1 squared is 1. So this is going to be divided by 12. And so this is also equal to expectation of sum of the xi squareds divided by n. Again, you can factorize out the summation in the end, so it's going to sum up n IID things. And we'll come up with exactly the same answer. Xi squared divided by n. Get rid of your I right here. This is going to sum up n identical things I'm dividing by n, so those n's cancel. And so what I can do with this, I shouldn't match these right away. I should say it's approximately true. Once I do the match, then I'm going to put a hat on top of the thetas. So from this, after I do the match, I'm going to wind up with sum of the xi squareds over n. That's my theoretical moment. And I'm going to say this is equal to 2 theta hat squared divided by 12. And so I can just solve, say 12 times sum of the xi's, I goes from 1 to n, squared, divided by n, square root over the top. Every time I do that, I always check to make sure everything is positive in here. It's all positive, because that's squared. So every time I do that, I panic for a second, and I check and make sure I can do it. The reason I panic is because when I see it on a midterm, I'm usually a little bit harsh about my grading on that. So you need to validate your answer makes sense. Then I'm going to divide by 2. Right here. And so this is going to be theta hat mod. And that's an estimator. And it's okay. I said that this estimator was unbiased last time. It's biased. So it's unbiased in the second moment. Because think about what we did. We matched the second moment. And so it's going to be unbiased in that second moment, but that's not what unbiased means. Unbiased is a condition on the first moment. So let me just ask a question. I told you the answer. Why is this biased? Jensen's inequality. It's unbiased in the second moment. And so what does Jensen's inequality say? It says something about bounding convex functions. And so the quadratic function is convex right here, so I can pull that exponent out, and then I have to figure out which direction to bound it by. How do I know that it's not equality? Because it's not a linear function. Jensen's is only tight when it's a linear function. Otherwise it's not. So this is guaranteed to be biased. So if I asked you this on a qualifying exam or a final, there's a really, if I could say, show that this is unbiased in the second moment, it's almost obvious because that's what you matched for it. So this was an equal sign when I wrote it down. Nothing's ever going to change that. And so on average, these things are still equal. Jensen's inequality, if I ended up asking you to show that this was biased, you could work out the first moment on that. That would be really hard to do. So take the expectation of this thing itself. So you've got expectation of square root over that. If you saw this on a test, you'd think, I've got at least an hour of math to do. So probably not the right way to do it. But if you invoke Jensen's inequality and had an argument, you'd be done in a minute. So keep that in mind. Easy ways to do problems, hard ways to do problems. So this is biased, but it's unbiased in the second moment. Jenny?
Because I can't see how we go from the last lockdown step to the last step.
From this step to that, I just back solve everything. Multiply by 12 over here, square root over the top, divide by 2.
Professor, we are taking 1 over n summation of the expectation of xi squared. And if I'm the n is going to cancel, why do we still have an n? I think I'm missing something.
So I only showed that the expectation of this theoretically was equal to that thing. But what I ended up matching was the stuff inside, right here.
Oh, you didn't match up with that.
So just think about that a little bit. It's always the thing inside the expectation that you're matching. So 2 different steps there. 9 o'clock in the morning. Okay, so that's method of moments. Yeah, let's check out max likelihood and see what it does. Now, saying that, this answer is like in the ballpark. If I had a ton of data, it'll be close to theta. And so it's not horrible, but of course, what we really want to do is we want to control these other objective things, like variance. How much variability is there in this estimate? And this estimate has way too much variability. MLE. This one's kind of fun. Step 1 is write down the likelihood. So the likelihood function I could write it down like this. What I usually do is I just write down the sampling distribution, the joint sampling distribution for everything. And then I think about it as a function of theta. I plug in all my x's into it, and I think about it as a function of theta. Of course, this is only defined up to proportionality. So likelihood functions are self-relative, they're relative to themselves. I read in the news the other day that the likelihood of something happening was 4%. And I think that's fine. but they don't mean the same thing I mean. So they're saying probability. So that's not what we mean in this class. So this is a curve over theta, and we'll look at that curve in a second. F of xi, the way we write it down, is going to be equal to 1 over 2 theta, the interval length. But I've got to be careful. Xi's live between negative theta and theta. And so when I'm thinking about likelihood functions, I'm thinking about the dependence between the data and the parameter space, what that functional relationship is. If that functional relationship is responsible for generating the data, I should use that functional relationship in inferring theta. For me, that's the likelihood principle, light. So it just seems like a good idea. That relationship is there. We know how everything is related. So why wouldn't we use that? If you think that's not obvious, if you go back to the early 1900s, this was heavily debated. And I'll bring you in a passage next time from a book that I have that talks about this argument. And so the things that we take for granted now weren't obvious way back in the day. So I've got to encode this into this thing. So if you ended up writing down the likelihood function, I'll write it down like this. The function over theta, so I build the theta over on the left. That's my convention. I don't know if in your university if they flow that. I mean the same thing. Yeah. I might just write it down notationally different. It usually takes me a day to unravel in this class, so we're just going to carry on. This is going to look like this. Product. I goes from 1 to n. 1 over 2 theta. And then I'll just write in this indicator function that the xi's live between negative theta and theta. So I'll build in that relationship. This part's still important. The 2 isn't, obviously. I could just get rid of that. So it doesn't help me at all. So this is going to be proportional to 1 over theta squared. If you wrote that down with the 2, no harm. I goes from 1 to n. Xi lives between negative and theta. And this is a rather clumsy way of writing down this indicator function because I've got a product over n things. So, yeah.
Shouldn't it be 1 over theta n?
Oh, did I square n? I think I was thinking about that too. So that's what that looks like. So it looks like this exponentially decaying function. So as theta gets bigger and bigger, that thing gets smaller and smaller. The question is what is the bound doing for us? If we think about the distribution itself, I'll draw it a little bit bigger. There's only 2 constraining points. So minus theta and theta. So I'm going to have a whole bunch of points in here. I've probably drawn them too uniformly. If somebody showed me that and they said they sampled it from a uniform distribution, I'd say no, you didn't. So I guarantee you did not do that. It should look more pocky. But you get the point. This is the min right here. And this is the max. We have notation for that. We've studied order statistics, so I'll call that x1 in braces. And this is x10 in braces. So those are the min and the max order statistics. So those are the things that budge up against theta. As long as I define those properly, I know everything else. x2, the second biggest thing, lives there. xn minus 1 lives right there. And they're bounded by these things right here, data points. So they're not bounded by theta per se. They still are. But they're bounded by something that I can think about a little bit more easily. And so really, this whole thing right here is just 1 over theta to the n. And this is a delta function on the minimum needs to be greater than minus theta, and the maximum maybe I'll just write it this way, that bounds that, and this is less than theta. And so that's my likelihood function. Let me ask you a question. What is the sufficient statistic here? You can answer in a way that's cheeky if you'd like. Well, it does matter. There's still an answer, but not quite that cheeky.
The one
Lower.
that's more extreme.
Yeah, so that's the minimal sufficient statistic. So you could have just said X is the sufficient statistic. So the minimal sufficient statistic, what is it? Pair rules onto something. Yeah, exactly. So let me just ask the question, is the min and the max the min? If I looked at this and I wrote this down, I might be inclined through the factorization theorem to say, this is the only thing that contains my data and the parameter, that's the part I'm always staring at, and I can't uncouple the min and the max from this. And so I might be inclined to say, I've got a two-dimensional minimal sufficient statistic. But you guys have already scooped me on this. And so it's really the one that's farther out and closer to this boundary that's going to tell us more about theta. So only one of these 2 points is telling us about theta. And so which one is farther out, how do you tell? Anna gave us an answer. Pair rules right about to say the exact same thing.
The magnitude.
Yeah, the magnitude of them. And that's because this thing is centered at 0. And so if I had a different origin right here, I would have to subtract off the origin. If you guys have been studying my qualifying exam problems, this is eerily similar to the circle problem. I promise I will not ask that this time. So just to let you know. But really that's just a three-dimensional version of this one-dimensional problem. And so you need to subtract off the origin in that problem. The origin is 0, presumably we know that. And so our likelihood function looks like this. It's exponentially decaying. As I get n bigger and bigger, this comes down even faster. And this thing is swooping up faster. So there's information there in n. This does not asymptote. It hits that wall right there. And so if I think about this in terms of a function of theta, I might just say, this is theta. This is going to be the maximum of x1 absolute value or xn. If that's not incredibly clear to you, here's an exercise you can always do. If you're playing around with these functions and I do something trickier, like I build this into a sphere or something like that, I made that problem probably too hard for a QB. So we won't do it this time. But I might ask a problem more like this to get the general glimpse, see if you know what's going on. If you ever see these things and there's all these conditions in here and you don't know what they mean, code it up. So if it's like something that's relatively small dimensional, and just plot it. So you can just check on like this would just be one dimensional, but if you're a higher dimensional, you can plot in those dimensions whether or not something's a 1 or a 0. And just check the condition and plot that thing and see what the likelihood function is doing. So that's my best recommendation. So in that old QE problem that you're probably studying, the maximum is on a plateau. And so it's kind of an interesting thing. So you can plot that. So that's what this looks like. And so where's the maximum likelihood? Here's a huge critical error that I see. 5 of you will do this. So on average. So I'm going to try to warn you and get you guys not to do it. Take a derivative over this thing. You cannot differentiate this. I've seen people differentiate this thing and remarkably come up with that as an answer. It's like, trust me, I will see that the equal signs don't connect all the way down your page. So you've got to check the boundary of the space. And so just in a rough nutshell, taking the derivative using that algorithm is not going to help you with this problem. All of those problems with parameters living on the boundary space will be like that. The boundary will define where the maximum is. So that's the MLE. So quick question from last time. What answer is better? This thing? It's biased, the answer. It's always going to be tucked in a little bit from theta. As I see more and more data points, those will push up against the boundaries. So I like this answer better, simply because it contains the minimal sufficient statistic. And the other one, because it doesn't contain those order statistics, I know can be beaten. Soon we'll learn about something called roundel equalization, and we'll formalize that with a theory. Any questions about this? I'd like to show you another example. Jen?
Professor, if I were given this question, how would I have thought about all of these things?
How am I going to think about how you think? I don't even know how I think.
I guess my question is, why would I go through this step to introduce indicator functions and all that to the likelihood?
Here's the real answer. Experience. You've experienced problems that are similar. So you've done enough problems that you can recognize what the right and wrong technique is. So I'm not sure. So I think that really is the answer. How do I know to do something? It's because I've been doing things like it before. So all the problems I'll fling at you on exams will be problems that are like problems that we've studied. Every time I see a problem that I've never seen before, it takes me quite a bit longer to, when does the idea jump in my head? I wish I knew which button I pushed, that it's like, I know the answer now. So you struggle with it until you build up enough experience. So I'm going to try to give you enough problems in this class so that you can have that experience for yourself. Okay, let's look at one more. This is in the book, so I'm not going to carve out all the details, but I would recommend you work through this. This is a very tempting problem to ask you on the next midterm because it's easy. So, and there's a few technical steps. So if I look at this problem, where I'm looking at a normal distribution, I've got n data points. I goes from 1 to n. The two parameters that I want to estimate are mu and sigma squared. Quick question, is this differentiable in mu and sigma squared? The likelihood function looks like this. It's going to be, I write equal, but I really mean proportional. Square root 2 pi, that's not going to help me. So I've got a sigma floating around out there. Maybe I want to put the sigma squared in here. E to the minus 1/2 xi minus mu squared over sigma squared. So I'd like my parameter to show up twice. In fact, I'm going to call this a v, just so I don't recognize the squaring as an operator. I'm thinking about it as a parameter. Quick question that I will ask you is, would it have mattered if I encoded this in terms of sigma instead of sigma squared? And the answer is no, it won't matter. There's an invariant property of the MLE. We'll state that next time and we'll prove it. I don't think we have enough time today. But it doesn't matter how I encode that. It'll still have the same maximum. So if I write this all down, I've got 1 over v to the 1/2. This is to the nth power, e to the minus 1/2. Sum of the xi's minus mu squared v. So if I were going to find the maximum likelihood estimators, I have to ask myself real quickly, can I differentiate this thing? Yes or no? Fair game? Is it smooth? Boundary conditions playing any issues? No. So these are well tucked inside of everything. They're not living on the boundary. Everything is smooth. I wouldn't go and take a derivative of this right away. I'd linearize it with a logarithm first before you do that. But when you do that, you'll wind up with mu MLE. So I'll have a system that I solve for. Two equations, two unknowns, two partial derivatives, 1 over v, 1 over mu. I'll set them equal to 0, and I'll wind up with v MLE. I'll throw the hats on here. This is going to look like this. Sum of the xi's minus x bar squared divided by n. This seems to be a big debate in Stat 101 classes. Divide by n or n minus 1. The MLE pops it out with n. You can verify that if you'd like. And so when you go to estimate variance, do you use this or do you use divide by n minus 1? Yeah. Anna uses n minus 1. Anybody else? What do you use? N minus 1. N minus 1. So this says something different. I'm going to argue to you later in this class, this is a far superior estimator. Okay, it's a little bit better. So the n minus 1 thing comes out of being unbiased, and that's a psychological contamination that we have, that we just want to do it. This actually has lower variance, and in terms of mean squared error, MSE, squared error loss, this is closer. So it's a little bit biased, but it makes up for it in terms of its stochasticity. So on average, this is actually better. We can't see that out of this derivation, but later on we'll see that. So method of moments. I would recommend you go and do the two partial derivatives. If you'd like me to do it at review session, which we will not do tomorrow, we'll do next week, because I think it makes a lot more sense. If you want me to do it, I can do it. But this is a calculation you're all capable of, and it's in the book. For moms, what we could do is we could match the expectation, or I could match the sum of the xi's. I should use all my data points, and I could match my sum of the xi's squared. I'll just point out, this is the exact same thing. This is the first moment, and this is the second moment. What am I going to actually match? I'm going to actually match the means. The means of the squared things and the means of the original things. So what is this? This is mu. What is this right here? So just remember, variance of x is equal to expectation of x squared minus expectation of x all squared. So expectation of x squared is equal to the variance, which is sigma squared. We've got a nickname for this. And I know what that thing is right here. This is equal to the expectation squared, the expectation of a normal model is mu. And so I can solve for this thing, that this is going to be mu squared plus sigma squared. Then I can just do my matching. So I'll do this real quickly. So mu hat mom is equal to x bar. This is x bar. Right here. Oops. I did this backwards, didn't I? Mu squared plus sigma squared. Wrong one. So I'll match this one using that equation. And then I'll go back and I'll match all of this stuff. So I'll take this thing, I'll substitute x bar squared in for that, and I'll solve for the sigma squared. So sigma squared hat mom is going to be equal to sum of the xi squared over n. I goes from 1 to n minus x bar squared. And that's just a rearrangement of this equation. You can go through that, that's also in the book. Quick question, what is this? You can work this out. These are exactly the same. It'll take you a minute to do. These are equivalent. Just expand the square, simplify it. You'll come back to that. So we get exactly the same answer this time, which is kind of cool. Let me just show you one more thing you can do with MOMs. This will just take 30 seconds. Here's another method of moment solution. And this is what I was talking about at the beginning of class. This thing s squared that we usually play around with is sum of the xi's minus x bar squared over n minus 1. So I could just write that down. Here's a method of moment solution. The expectation of s squared is equal to sigma squared. You've proved this at least once or twice in your life. And so, again, this is just an algebra problem. And so what that means is we could match this thing directly to that. So method of moments applies to this. It's a function of the moments. And so that would be sigma squared hat is equal to f squared. So this is a game that I play all the time in statistics. Is I ask myself when I see an estimator that works well, is there a way of deriving this using MOMs? Is there a way of deriving it? MLEs doesn't give you any choice. But I'll ask you one more question, and this is the question I really always grapple with. If I like a solution, is there a Bayesian way of deriving it in which priors would correspond to that? I'll give you a hint, and I'll come back next time. There is a Bayesian way of deriving this. It uses the flat prior on mu, and it uses the scale invariant prior 1 over sigma squared, 1 over v on variance. I'll spend 15 minutes talking about that next time. And we'll talk a little bit about that. I may quiz you on that on the Q. And so I'll just give you the answer to it, and we'll work through it real quickly, and I'll leave you with a few details. Then we're moving on to EM. So big switch of gears, then we'll come back around to theory. And we'll formalize all of these comparisons. That's it for now, you guys. If you're on the schedule, I'll see you later today. If not, say hi.